Good afternoon, one and all. Hope you're all healthy at home and are taking care of yourself. So we are going to continue with our chapter 5, and we were discussing about the Fredholm theory of compact operators, and we did certain lemma and propositions. And in this lecture we are going to discuss about another proposition 5.2.4. What is the statement of the proposition? It is actually states that for every epsilon greater than 0, there exists finite number of linearly independent eigenvectors corresponding to the eigenvalues lambda I, with mod lambda I is greater than or equal to epsilon. So if you are given any operator, and then for every epsilon we can find corresponding eigenvalues of that operator, say lambda I. Okay, all these lambda i's such that mod lambda I is greater than or equal to epsilon. Okay, all these eigenvalues which satisfy this condition will have only finite number of linearly independent eigenvectors. Okay, so from this what can we say? We can say that there exists actually finite number of lambda I belongs to sigma p. Sigma p is the eigenspectrum, right? Or the point spectrum. So there exists finite number of lambda I belongs to sigma p with mod lambda I greater than or equal to epsilon. Okay, or we can also state that, and also we can conclude that dimension of kernel of t lambda. Here t lambda is a notation. It is actually denoting t minus lambda I, the operator t minus lambda I. Okay, t lambda is nothing but the operator t minus lambda I. So the dimension of kernel of t lambda, that is t minus lambda I, will be less than infinity. That is, it will be finite. That is, kernel of t minus lambda I is actually nothing but the eigenspectrum. It is related, right? So from this proposition we can conclude that the dimension of kernel of t lambda is finite, and also there will be only finite number of linearly independent eigenvectors. So let us see how we can do the proof of this. So this also we are going to prove by the method of contradiction. So that is, I am going to assume that there is infinitely many linearly independent eigenvectors. Okay, so suppose there exists xi where I varies from 1 to infinity linearly independent vectors, okay, such that t of xi is equal to lambda I xi, where modulus of lambda I is greater than or equal to epsilon. So that is, I am considering there are infinitely many eigenvectors, right? So for each lambda I greater than or equal to epsilon, I am considering xi are the vectors which satisfy t of xi is equal to lambda I xi. That means xi's are the eigenvectors. So there are infinitely many eigenvectors. Okay, now consider the notation ek, which is equal to span of xi I varies from 1 to k. So it is a linear combination of these eigenvectors, and that is clearly contained in ek plus 1, right? Now we have infinitely many eigenvectors, so we can consider the spaces ek plus 1, ek plus 2, and so on. Okay, now by the lemma I had stated that we will be using this lemma very often. So by the lemma 5.2.1 we can find yk an element of ek, okay, such that norm of yk equal to 1 and distance of yk and one space less than this ek minus 1 is greater than or equal to 1 by 2, right? That was our lemma. By lemma 5.2.1 I am considering an element yk whose norm is 1 and whose distance from ek minus 1 is greater than or equal to 1 by 2. Now we have to show that there is that set is linearly independent, right? So if we have the set is finite dimensional. So if we have taken the contradiction, we have to obtain some contradiction. So for that, what we are going to show here is we will show that T of yk by lambda k, okay, does not contain Cauchy's subsequence, okay, Cauchy's subsequence. So this is what we are going to prove. Now if this we'll see what we'll get in the end. So now look at this element yk by lambda k. Norm of yk is 1, right? So it is bounded. And we know that modulus of lambda k is greater than or equal to epsilon. So this implies 1 by mod lambda k will be less than 1 by epsilon, right? So this term or this is a bounded sequence, okay. This sequence is bounded if we consider, therefore the sequence yk by lambda k is bounded, right? So now this is bounded. So for any bounded sequence, I am going to show that T of that particular sequence does not contain a Cauchy subsequence, which implies that T is not compact, okay. T will not be a compact operator. So that will be a contradiction for us because we are considering compact operators. So now let us see how we can show that this does not contain a Cauchy subsequence. So for that, what I'm going to do is I'm going to consider yk is equal to summation k equal to I equal to 1 to k ai xi, okay. Then what will be T of yk by lambda k is a constant or a scalar. T of yk will be nothing but T of summation ai xi. I varies from 1 to k, okay. This is whole divided by lambda k, that is this is nothing but a1 T of x1 by lambda k plus a2, T is an operator, right? So we can take it inside, x2 by lambda k etc. plus ak minus 1 T of xk minus 1 by lambda k and plus ak T of xk by lambda k, right? This is how this T, the operator, acts on yk by lambda k. Now all these terms I'm going to sum up. This is I equal to 1 to k minus 1. Now we know T of xi is nothing but lambda I xi, right? So this is ai lambda I xi by lambda k. Now what will happen to this kth term? T of xk is lambda k xk. So lambda k and lambda k gets cancelled. So I'll get ak xk. Okay, right. So this is our expression. Now I'm going to simplify this expression and write as T of yk by lambda k is equal to yk plus zk, where zk is an element of ek minus 1. I hope you are getting the picture. That is, yk was, we had chosen yk to be summation I equal to 1 to k ai xi, right? And we have obtained that T of yk by lambda k was nothing but, I'm just explaining it again, it was nothing but ak xk. This term was there, that is a kth term was there, and summation of k minus 1 ai into lambda I xi by lambda k. Sorry. So that is it is the linear combination of xi's where I vary from 1 to k minus 1. So ek minus 1 is nothing but span of xi where I varies from 1 to k minus 1. So I can consider this term to be an element of zk, right? So yk is the summation of all these terms, so all these terms together. So if I just expand this is nothing but a1 x1 plus a2 x2 plus etc plus ak xk. So except this term, the rest of these terms can be added or it can be included with this zk, or it can be considered as an element of ek minus 1. So altogether I can write t of yk by lambda k as yk plus zk, where zk is an element of ek minus 1. Okay, so I hope it is clear. Yk, when we expand, we will get this expression. So all these remaining terms except ak and xk, ak xk as an element of, can be considered as an element of ek minus 1. So this term and this term together can be considered as an element of ek minus 1. So I can write t of yk by lambda k to be yk plus zk. Okay, so let's see whether it is having a Cauchy's subsequence or not, and so on. So for k greater than n, okay, we have norm of t of yk by lambda k minus t of yn by lambda n will be nothing but norm of, what was our, yk plus zk minus yn plus zn. Right here zk, zn and all are elements of ek minus 1, and since n is always less than k, it will be either k minus 1 or k minus 2 or any other thing. Now en will be something like a span of xi where I varies from 1 to n. Right here n is less than k. So I can rearrange this and I can write this as this yk, okay, minus yn minus zk plus zn. I'm just combining these terms because all these terms can be considered as an element of ek minus 1. Okay, zk and zn are clearly chosen to be elements of ek minus 1. Now yn, since n is less than k, it can be any values like k minus 1, k minus 2, etc. But k minus 1, if it is an element of k minus 2, it will also be an element of k minus 1. That is how we had chosen our subspecies e. So that is the distance between, or the difference between yk and an element of ek minus 1. Now we had seen by lemma, this is always greater than equal to 1 by 2, right? By the lemma we had assumed that distance of yk and ek minus 1 is greater than equal to 1 by 2. So clearly this cannot be a Cauchy's sequence. Thus there exists no Cauchy's subsequence of t of yk by lambda k. So which implies that this does not have a Cauchy's subsequence, means t is not compact, which forms a contradiction. We are dealing with compact operators only, so this is a contradiction, and thus our assumption was wrong. What was our assumption? We had assumed that the space will be, or the set of eigenvectors will be correspondingly infinite dimensional, right? So that was the proof. What we did was we had chosen, we formed the subspaces, and we formed a sequence which was bounded. We found a sequence which was bounded with the help of the formula or the inequality that mod lambda I is greater than equal to epsilon. And then we showed that T of that sequence cannot be Cauchy's. So in turn, T cannot be a compact operator, which contradicts our assumption. And therefore what we had considered, that is the set of linearly independent eigenvectors is infinite, will turn out to be false. So that was our proposition of today. So just recall or go through the proof again, and just keep this proposition in your mind. So that's it for today's session. Thank you.